Hello, it's Mr. Claudia here, and today we're going to complete our review of the function section by looking at inverse functions. Again, this is a pretty short lesson, which gives us a useful strategy that we'll be using when we look at logarithms later in this chapter. It's not a terribly difficult concept, but IB does like to bring it up, especially because it has a unique notation. When you hear the word inverse, you probably think of opposite. Now, from a math point of view, we tend to think of inverse not as an opposite, but as something that reverses an action. So here's my kind of illustration of an inverse. You have a function, f, and you have an inverse function, f at -1. If you put an apple into function f, black box, it spits out a lemon. Well, the inverse function takes that lemon as an input and spits out an apple. So it undoes the function. The inverse function is written like this. Again, it's a very specific notation that you're going to have to be comfortable with. The way we would read this is not f to the -1. This is f inverse. That's how we say that. And be careful. It does not mean one over f of x. You have learned that a -1 exponent, we're going to talk about this in our next lesson, -1 exponent means, or a negative exponent means that this would go into the denominator. That is not true, though, for an inverse function. This is just a notation. So it doesn't have anything to do with exponents. It's just how we denote the inverse function. And yes, it reverses the action of a function. So again, if I didn't want to use apples and lemons, you can think of x going into the black box of a function. And that black box spits out a y. Well, the inverse function takes the y into a black box and spits out the x again. Okay, so let's look at how the inverse function, what it looks like algebraically, and then we'll look at graphs. But algebraically, we find that the inverse function, the very easy strategy. We exchange the y's with x's and the x's with y's, and then we solve. So let's look at this example. F of x equals 2x plus 3. Find the inverse function. Okay, well, for function y equals 2x plus 3, the strategy is we exchange the x's and y's. So we get, okay, I'm going to turn that y into an x and that x into a y, and I get that expression. And now solve for y. Okay, well, to get the y by itself, I have to first do reverse BEDMAS, so I get bring the 3 to the other side, so I have x minus 3 equals 2y. How do I get the y by itself? Well, I divide both sides by 2. So I end up with y is equal to x minus 3 over 2. So if the question was not asking for y, it was asking for the inverse function. So I should write f inverse is x minus 3 over 2. And there it is. It's not a difficult procedure. You always just exchange and then solve. The inverse undoes the effect of, since the inverse function undoes the effect of the original function, what happens if I have FOF? And now we're really combining notations. FOF, we learned this yesterday, this is a composite function. Let's rewrite this into something that's easier to understand. This is f at f inverse of x. So what happens if I sub the inverse into my original function? Okay, so that's essentially going to be, what happens if I sub x minus 3 over 2 into 2x plus 3? So I'm going to replace all the x's with x minus 3 over 2 plus 3. So that's, okay, so if I if I'm multiplying here, the 2's cancel out, so I end up with x minus 3 plus 3, so that just gives me x. So if I want to do a composite function, a combined function of f and its inverse, I end up with just x. In other words, x goes in, and then x comes out. There's no change to x. And that's exactly what we kind of explained up here, right? If I put in an apple into a composite function of a function that's inverse, I get the apple back out. X goes in, x comes out. IB does kind of stress this little point, but I don't think it comes up too often, but we'll just make a note. A function that leaves x unchanged is called an identity function. In other words, I at x is equal to x. And f composite inverse is an identity function. I don't find this point comes up too much, but we're just going to make a note of it. An identity function is a function that doesn't change x. So x comes in and x comes out. So this composite function, f and its inverse, well, that is just an identity function. The identity function will come up in first year university when you're looking at matrices of many different systems of equations. You'll learn more about identity functions, but at least we've introduced the definition here. And of course you get a great joke, right? If I have a function, a staple function, and then I put that into a staple remover function, well then I just get staple out, right? Nothing, neither stapled nor it's just x goes in, x comes out. If that makes any sense. Okay. Now graphically, if I have this function f at x equals 2x plus 3, I put in the value x. Okay, so that's going to give me 2 plus 3. So that's going to give me an output of y equals 5. To undo this function, I would use my inverse function. I put in the input of 5, so that gives me 5 minus 3 divided by 2. So that's 2 divided by 2. That gives me y equals 1. So the point on the 1, 5 on f at x becomes this point 5, 1 on the inverse function. It's basically I switch the x and y values, or I reflect around the line y equals x. So we're just going to write that out. In general, the graph of the inverse function inverse of a function is the reflection of the function about line y equals x. So if I want to easily graph an inverse, I can do that by one of two ways. I can draw a line y equals x, and I can just reflect, imagine this is a mirror, and I can draw my mirror reflection over here. Or I can look at each point and switch the x and y's. So this is 0, 5. That's going to become 5, 0 on my inverse. I'm going to do my inverse in blue. So 5, so it's going to be somewhere here. This point gets mapped now here. This point, negative, what is that? Negative 2, 0 becomes 0, negative 2. 0, negative 2, so it's here. Oh, and then it's very clear to me. I can draw my new line segment. So when you're trying to draw the inverse, two methods. One is to draw the y equals x and try to reflect it yourself. And again, if you think through it, you should be able to figure it out. Or if you want to be more numerical, you can take all your points, switch the x's and y's, and then plot them on the graph. Whatever works for you. This one's nice because we know some points. This one we don't. So again, there's a few ways of doing it. Let's draw that y equals x line again. Okay, so if I want to reflect, still gets a little confusing. What I find can be useful, okay, so this is probably negative 2 and 5. So it's going to be 5, negative 2. So this peak is going to be here. Negative 2 and 5. So 5, negative 2, yeah, so somewhere here. And then that goes through 0, 0. And then it goes to, say, negative 5, negative 5. So it still goes here. And then this is 1, negative 2 maybe, so negative 2, 1. And then it goes 4 and 5, so 5, 4. So this is going to go up like this. Oof, that's hard. That's a tricky one. I actually chose a really hard example for us, but just so you get an idea of how you do it. You'll notice that all the points on y equals x are on y equals x in the reflection as well, because they don't, we just switched if y and x are the same, when we switch them, they'll still be on this line. You'll note that this goes into the negative y direction. Now it's going in the negative x direction. This goes in the positive y direction. It's going in the positive x direction. And if you look at that mirror, you can see that it's reflection in the mirror. Tough question though. Now the one final thing to look at is the inverse. Actually, we should label these as the inverse. Is the inverse a function? Well, remember, to pass to know if it's a function, it has to pass the vertical line test. If I run a vertical line through the blue curve, that inverse function, I see that there are several places where it intersects the line more than once. So therefore, it is not a function. It does not pass the vertical line test. I probably could have known that if I just looked at my original function and looked at a horizontal line test. If the function doesn't pass the horizontal line test, in this case you can see the horizontal line goes through more than 2 points of the graph. Because it doesn't pass the horizontal line test, I know that the inverse function will not actually be a function. So let's just make a little note of that. A function must pass a horizontal line test to have a valid inverse function. Oh boy. Okay, there we go. A function must pass a horizontal line test to have a valid inverse function. Hopefully that didn't confuse your understanding of inverse functions. Should just be mostly a review, and your homework for today is page 20, number 1 to 7. Good luck, and we'll see you next time.